This is lecture 38, and in this we want to understand the how if you have a graded module over the polynomial ring over an Artinian local ring, like in the last lecture, how the length of the module. So we know that we saw that each mj is a finitely generated R module. R is an Artinian local ring. Hence, mj itself is an Artinian module, so it has finite length, and we would like to understand how it varies with j. Okay, so the function j goes to length of mj. This is what we would like to understand. So we want to define polynomials. Pk of x is a variable, to be the formally like the binomial coefficient x choose k, but if you write it out, what is it? X times x minus 1 up to x minus k plus 1 over k factorial, and this is a polynomial with rational coefficients. Okay. We can take a quick look at what this is. P0 is just x choose 0, so there is nothing terms here, so this is just 1, constant polynomial 1. P1 is x choose 1, which is just x, and then and so on. Okay. So degree of Pk is k. Okay. And these are okay. Yeah. Definition, some notation. Let f from z to itself be a function. Write the first difference. Delta f to be the function for the function which takes n to f of n plus 1 minus f of n. Okay. So this is what okay. So we would need to so if you take delta of pk, okay, is just pk minus 1 for all k greater than 0. That's just like Pascal's triangle. Okay. So what we are what we are saying is n plus 1 choose k minus n choose k is n choose k minus 1. Okay. N plus 1 this follows from the Pascal's triangle. Okay. And also if delta f is P, so maybe one should not just one should think of f of x as a polynomial in Qx. So we would like to talk about delta f for if delta f is pk minus 1, then there exists a c in Q such that f is pk plus c. Okay. So this is slightly loose. What we are saying is f is a function from z to z. It agrees with pk at every point of z. Okay. So this is a polynomial. So delta as a function from z to z, these two things are the same. Okay. F is a function from z to z. Okay. It's the same thing is implied there also. Okay. So this is two observations. Okay. So here is a lemma. Let f be a rational polynomial, okay. Then the following are equivalent. 1, okay. F is a Z linear combination of the pk, polynomials pk, to f of n is an integer for all n in n. 3, f of n is an integer for all n sufficiently large, and 4, the function delta f satisfies 1 and there exists an n such that f of n is an integer. Okay. So the conditions are f itself is a linear, so we are talking about a rational polynomial. F itself is a linear combination of the pk. Okay. Then that implies, okay, I mean, it is equivalent to f of n is an integer for every n, and this is a weaker statement. And as far as this is concerned, this is a weaker, this just says there exists n with this property, but on the other hand, one also needs that delta f satisfies 1. Okay, so let's quickly prove this lemma. Okay. Notice that pk satisfies this. Pk of n is just n choose k, which is an integer for all n in n, all n in z. Okay. Therefore, every z linear combination of the pk also has the same property. So this is 1 implies 2. Okay. 2 implies 3 is immediate. Okay. Now let's prove 1 implies 4. Okay. That is also immediate because delta f is, so if f is some nkpk, then delta f is nkpk minus 1. Okay. So this is, it's also true that 1 implies 4, delta f satisfies this, and f of course satisfies any z linear combination. It's true, I mean, f satisfies 2, condition 2, so it also satisfies 4. Okay. The final part of 4. Okay, so now let's prove that 4 implies 1. Okay, so this is to say that if delta f satisfies 1, so let's go back. If delta f satisfies 1 and it has this property, then f itself satisfies 1. Okay, so write delta f as some ekpk, then f, we have seen this earlier, f is ekpk plus 1, pk goes to pk plus 1, ek doesn't change in any way, plus some e0 for some e0 in q. However, since f of n is an integer, we are just assuming that right, these are integers. That's for the f of n satisfies 1 is to say these are integers. Okay, so f of n is an integer, e0, which is f of n minus ek pk of n, and this is in z, is an integer. Okay, but that we can rewrite. Okay, as k plus 1. Okay. So this is originally it started from k equals 0 to some d, whatever d is. Okay. So so now we can rewrite it as E0 times P1 plus this condition. And so it's so this proves 1. Okay. We notice that E0, maybe I should just write it. Notice that here we only start with P1 onwards. So E0 is E0 times P0. Note. Okay. So therefore F is P E0 P0 plus sorry, indexing is some slight issue. Let's write this as I equals 0 to D. Call this thing E prime. I apologize. E prime. Okay. And so this is E prime. Okay. E prime P0 plus EK PK plus 1. K goes from 0 through D. Okay. So this proves 1. Okay. So this proves 1. Okay. So now we prove that 3 implies 1. Okay. So this is done by induction on degree. So we assume that so 3 so the assumption is that f of n is okay, since f of n is an integer for all n sufficiently large, okay, delta f of n is an integer for all n sufficiently large. Okay, so by induction, f is a delta f satisfies 1, and satisfies 1. And of course, so therefore 4 is satisfied. Satisfies 1, so 4 is satisfied. Delta s satisfies 1, and f of n is 0 for f of n is an integer for some integer. So 4 is satisfied. But we have already proved that 4 implies 1, therefore 1 is true. Okay, so this is it. Okay, so next. So we want to apply this to the study of what is called the Hilbert function of graded modules over polynomial rings or over Artinian rings. So this is the setup that we want. So let's say Hilbert functions. Okay. So we go back to the setup that we had earlier. So R is an Artinian local ring. S is a polynomial ring over R in n variables and graded with degree of xi equals 1 for all I. And M is a finitely generated graded R module. Okay. So, okay. So the function, so we noticed that, we saw that, so we can rewrite this as M, we can decompose M as Mj as R modules. Okay. Notice that this decomposition is R modules. Similarly, direct sum of Sj as S is as R modules. Okay, so we saw that Mj is a finitely generated R module for all j. Therefore, since R is, so far we didn't use that R is Artinian. We used that M is Noetherian, for which we use that S is Noetherian. To say that Mj is a finitely generated, we have to take submodules and then their quotients. So we need all of them finitely generated. So we needed the fact that M is Noetherian. For M to be Noetherian with this hypothesis, S has to be Noetherian, for which all that we need is R is Noetherian. Okay, so we are not yet used at R is Artinian. So here we set that up. Okay, therefore, for all j, Mj has finite as an R module. Okay. The function definition, the function, let's denote it by h sub m from z to itself, which takes an integer j to the length over R of m sub j, okay, is called the Hilbert function of M. Okay. So what we want to prove is that, so we will prove that there exists a polynomial P sub m, it depends on m, P sub m with rational coefficients, okay, such that for all j sufficiently large, Pmj is the Hilbert function of m at j. Okay. So this is what we want to prove. So we will prove this statement. Okay. So this is called Pmj. Pm, the polynomial, is called the Hilbert polynomial of m. Okay, so we want to, so okay, so this is this, and in the little this lecture, maybe a little bit of the next, we will prove that so Hilbert function is what is defined, that there is a polynomial which gives a value for sufficiently large n. Okay, so we will see example where and it is not at all difficult to generate them. We will see examples where the polynomial won't agree with it right at the beginning itself. Okay, so that's one thing we will have to, that's okay, we only, that this is for all sufficiently large. Okay. So we will prove something a little stronger. We will say that we will prove that the Hilbert polynomial is actually a combination, integral combination of the of these here. Okay. That's the context of this lemma, that the Hilbert polynomial is a Z linear combination of the pk. That's what we will prove in the theorem. The full strength of the theorem will not be used a lot, but it's better to see it this way itself. Okay, so let's prove that statement, theorem. let R be an Artinian local ring. Okay. S is a polynomial ring over R. M finitely generated graded S module. Then there exists integers E0 through En minus 1. So notice it's minus, if there are n variables, this will go up to n minus 1. In other words, there are n coefficients, okay, such that the Hilbert function of M in degree j is equal to Ei, Pi is thought of as a function from z to z, j, I goes from 0 to n minus 1 for all sufficiently large j. Okay, so this is the stronger version of this theorem. Okay. In other words, the Hilbert polynomial is an integral linear combination of these special binomial polynomials that we just defined. Okay. So this is what we will prove. So we'll set up the basic part today in this lecture, and in the next lecture we will prove this by we will finish the proof. Okay. So this proof, the just setup of the basic part of the proof will be done. We'll do it now. Okay. So this is proof by induction on n. N, the number of variables. Okay. The base case is n equals 0. Okay. In other words, S is R, and M is a graded module. It is finitely generated as an S module, means that it has generators living only in finitely many degrees. So in other words, so since M is finitely generated, now also as an R module, because this is R, okay, we see that Mj must be 0 for all j with sufficiently large j and sufficiently small j. Okay. Going in either direction, Mj must be 0. Okay. In other words, Hilbert function of M in degree j is 0 for all j sufficiently large. It's also true. Okay. So we just need this part because the assertion is only about this. And we treat this as a polynomial, as the empty sum on that side. Okay, so this we treat as okay, so this we take. Okay, so this is a constant 0 polynomial. Okay, so this agrees with the remember n is with the constant 0 polynomial, okay. And that's all. Here the summation is empty. Okay. So this proves in the 0 case. So let's just look. If this thing says that if there is one variable, you will only see P0, which is the constant, okay, constant polynomial. If there are two variables, we will see P0 and P1, which is constant and linear. Okay. If there are no variables, then we won't see anything here. And we get this convention, sum of an empty set is 0. Okay, so this takes care of the base case. Okay. now assume that n is greater than 0. Okay. Now consider the map m goes to m multiplication by xn. Okay. Let's look at the kernel and co-kernel. So call this map phi. Okay. Notice that kernel of phi xn kills xn times the kernel of phi is 0. That's why it is a kernel of multiplication by xn. And similarly, xn kills the co-kernel also, co-kernel of phi. So xn times the kernel of phi is 0, xn times the co-kernel of phi is 0. Because xn co-kernel means m modulo the image of this map, but anything that is in m will get multiplied by xn precisely into the image of this, so it will go to 0. Co-kernel will be 0. So in other words, kernel of phi and co-kernel of phi are modules over S modulo xn, okay, which is isomorphic to the subring R adjoint x1 through xn minus 1. Okay. So this is both a subring of S and also a quotient ring of S, and we will identify these two things. It's okay, we will not fuss about this. Okay, so we get this. Now, okay, phi preserves, phi is a graded map, graded homomorphism, okay, changing degree by 1. Okay, so that is phi of a homogeneous element, of degree j is a homogeneous element of degree j plus 1. Okay. Therefore, kernel of phi and image of phi are graded. Kernel of phi and image of phi are graded submodules of M, okay, which now implies that co-kernel of phi is a graded S module, okay, and all of these are finitely generated because we are in an Euclidean situation. So therefore, kernel and co-kernel, kernel phi and co-kernel phi are graded finitely generated modules over R adjoint the first n minus 1 variables. Okay, so we will end this lecture here, but so there's a little bit more argument using induction to now conclude the proof, which we will do first thing in the next lecture.